The two accelerators of the Ruđer Bošković Institute in Zagreb can provide a wide range of accelerating voltages, from only 50 kV up to 5 MV. Each of the accelerators has two ion sources, enabling acceleration of ions of almost all elements of the periodic table. Ion beam irradiation and ion implantation are useful for different applications, mostly related to material science. The dual beam irradiation for fusion materials, or DIFU end station, is designed primarily for irradiation of fusion materials, but it can be used for any other type of irradiation or implantation. Irradiation experiments are typically conducted to create radiation damage in the target material, but they can also be used to implant a certain dose of specific atoms into the specific depth of the material. The DIFU end station can accept ion beams from both RBI accelerators independently or simultaneously. Any samples of up to 3 × 3 cm² in size can be irradiated. A primary aim of the DIFU scattering chamber is irradiation of materials used in fusion reactors such as steels and tungsten. In that case, dual beam irradiation by heavy ions and implantation of alpha particles is typically used. Another important topic is irradiation of materials exposed to solar radiation in space, for which proton contribution is the strongest one. Finally, the same setup can be also used to implant small doses of a specific element into substrates like silicon and diamond. The chamber cannot be used for any analysis method, though some in situ monitoring of the process is available. The samples are mounted on a movable sample stage or on a heater if high temperature is required. The sample stage is large enough to mount several samples at the same time. The beam is passed into the chamber onto a piece of scintillating quartz. If needed, the beam is passed through a beam degrader system which reduces the beam energy. In this way, a more uniform implantation of ions can be obtained. Movable slits define a rectangular scanning area, and electrostatic scanners are used to distribute the beam uniformly. A pair of Faraday cups, one for each beamline, is lowered to collect the exact ion beam current. Once the current is measured, irradiation can begin. A current readout from the slits measures the edges of the beam shape. For longer irradiations, the current is periodically checked with the Faraday cups. For high temperature experiments, the temperature is also monitored with thermocouples and an infrared camera. Some experiments require high quality vacuum, and this is checked using a residual gas analyzer. The sputtering slots can provide many elements, but cathodes need to be prepared in advance. We can use current from 100 picoamperes to hundreds of nanoamperes depending on the ion. Doses from 10 to the 12th to 10 to the 16th ions per centimeter squared can be achieved. If you want to learn more, please visit the CERIC website.